Solution equilibrium, that's at a saturation point. The rate of dissolving equals the rate of crystallization. We've mentioned solubility and saturation points already, guys, when we analyzed solubility curves. On those curves, when you were saturated, you have dissolving and recrystallization forming. Do you see that process taking place with the naked eye? No. Okay, but it's happening when you're at an equilibrium point. Again, it has to be in a closed system. So unless it's closed, you're not going to get to it because you've got pressure, you've got temperature always affecting it. Okay? Think back to that video I showed you guys about a triple point. Remember that triple point video that I showed you where it was constantly, right? It was, yeah. Okay, now that was a closed system to an extent, but then it also brought in heat from the outside of the container, which then got the cycle to go again. All right? But you get the idea. It's the best we can do because there's always going to be a transfer of energy. Okay, there's always going to be that transfer of energy no matter how closed the system you may think it is. All right, chemical equilibrium. I don't think that we talked about this yesterday. Okay, it's the rate of the forward reaction equals the rate of the reverse reaction. So there's really two types, and we're going to talk about those and show those. And you guys are investigating these in lab. Or the rate of breaking bonds equals the rate of forming bonds, if we're thinking about it like that. That's how the rate of the forward reaction equals that rate of the reverse. Okay, you're breaking bonds and you're forming them all at the same rate. So this picture I have up here, you guys have a better one in your notes. We'll talk about it in just a second after everybody gets them down. If you were to graph and see what's happening in equilibrium, there's two types, okay? So we started talking yesterday. You guys started seeing this. You're going to see it more today in lab, next period, okay? If we're talking about a rate, okay, the rate of the forward reaction equals the reverse reaction rate. That's rate equilibrium. So that's this one right up here on the top, okay? If we're talking about equilibrium in terms of concentrations of reactants and products, this is what we would see on the bottom, where you have no change in the amount over several data points. So you guys were seeing the bottom one in lab the other day where your concentrations, when you had them 3 or 4 times in a row, that's when you knew you reached equilibrium. Now, the first set, they probably also experienced the top. When you guys go to graph your data, you will see graphs that look like this. All right? So we think that, equilibrium means that, they have to be equal, the same amount. That's not the case. Constancy is what we're looking for. Okay? That's when we know equilibrium has happened. So if it's rate, you're going to see that top graph. But if we talk about in terms of concentration, add that to your notes down here. Like concentration / amount of products. Okay? That's what you might see where you have a leveling, that plateau effect. All right, with the amounts of reactants and products. Does that make more sense? Okay? So as you're going through the lab, you may think, this is weird, I'm doing something wrong. No, you may not, because there's 2 different types of reaction or equilibrium. LeChatelier's principle, guys. Stress is what you want to think about. Right? We're all familiar with stress. This is not on the next page of your notes. It is on page number 14. So guys, LeChatelier's principle explains how a system at equilibrium will respond to stress. All right, it's showing us how it's going to respond to stress. There's different types of stress. They can be any change in temperature, concentration, or pressure when you put them on a system. So you've got that closed system, it reaches equilibrium, and then it just kind of stays stationary. Well, if we put something else into the system, we got to see, what would happen? And that's what we're looking for. So when that stress is added, the system will shift in order to relieve the stress, meaning they will shift toward the product, so it's going to move or start reacting more where you're combining the reactants to make more products, or it'll shift away from the product side of your reaction and shift back toward the reactants and reproduce those. The shift is either an increase in the rate of either the forward or the reverse reaction. All we're going to have to do, guys, with LeChatelier's is you're going to be given a stress, and you have to tell me, does it shift to the right or does it shift to the left? Okay, that's it. It's simple. It seems confusing. I promise it will click for you guys, each one of you, at a different time. but the more you do, eventually I promise it will click in for you. So if we shift to the right, it means we shift toward the products. We start making more. That's where the rate of the forward reaction will increase. Okay? Where you could see it symbolized with something like this. Okay? Where the top arrow is bigger than the bottom arrow, meaning, oh, we're moving toward the product. It favors the products being formed. Okay? It favors the products being formed. If we shift to the left, it means we go toward the reactants, where our bottom or our left arrow would be bigger because the reactants then are going to be favored. So the first type of stress we can change is concentration as an initial stress. So that means we can. It's going to shift when the reactant or product is added or introduced. You guys are going to do this today in lab. Okay? We're going to get to equilibrium, then we're going to either add something or we're going to take it away, and we're going to see how that affects our reaction rate. So when the concentration of a reactant or product is increased, we're going to move away. So guys, if you're going to increase something, the analogy that I use is like a seesaw. You know what a seesaw is, right, teeter-totter? Okay? No, not sea salt. Seesaw. All right? It's kind of like a balancing act, okay? So as we get into this, it'll make more sense. But guys, if you increase something, okay? If we were to increase ammonia here in this reaction, that means we have a lot more ammonia. Well, what's it going to do to try to overcome that? We want to be back at equilibrium. So the way I think about it is, now it's imbalanced. So if we were to look at this is my, when I'm at equilibrium, okay, I've got a nice balanced seesaw, okay? But if I add more, that's not going to work. I'm not even going to try and draw it on here. So example number 1, we've got that reaction. Okay. What type of reaction is this? Let me just ask that. Why XO, Grant? Yeah, there's energy. It's written as heat, but remember that means the same thing. Number 1, if we add H2O to the system, the system would shift to the blank. Okay. So let's think. Where is water, guys? Reactant or product? It's a product. It's right here. If I add more of that, which side of the reaction? Am I going to shift toward the left, meaning more toward reactants, or is it going to shift to the right toward my products? Okay? Well, let's think. Okay? We're adding this. So that means the amount of water is increasing. Think about it visually like a seesaw. Okay? Products over here, reactants right here. It's going to go like this, right? It goes down, but we're not looking at what happens, guys, when you add it. We're looking at where does the reaction now, after you add it, have to shift to equal out again? Toward the reactants, right? So I'm not asking you where does it go when you add something, okay? So everybody said right there because, water was a product. Doesn't mean we're shifting that way. After we add it, we got to go away from where we added it to. So we added it to the product side, which means we're going to shift to the left. We're going to shift away from where we added it. Again, with our balance being, our midpoint being the reaction, the yield sign. Okay? So we would shift to the left. What's going to happen to the concentration of ammonia gas then if we shift toward the reactants? Think about what we're doing here, guys. We're shifting this way, meaning we're going to produce more reactants. What's going to happen to the concentration of ammonia? It's going to go up. It's going to go up. You guys have never done this before, have you? Okay, so this is brand new. It's going to take some time. The more we do, the better, easier it's going to be. Let's take a look at number 2. I'm going to erase all my little notes here, and we're going to start fresh. Okay? Number 2 says, if we add oxygen, is oxygen a reactant or product? It's a reactant, okay? So we're increasing the amount of oxygen we have. Think about, okay, now it's imbalanced. The reactant side, guys, has sort of gotten, quote-unquote, heavier because you have more of it. Where does the system, the overall reaction, then have to shift to balance back out? It's got to shift toward the products, okay? So to the right, toward the products, which means what? What are you going to start making more of? Hold on, I'm not asking NO, okay? Just in general, if we're going to move to the right, we're going to start reacting in the forward reaction. What's going to go up? The products. Your concentration of all your products will go up. What's going to happen to your reactants concentration? they're going to do the opposite. They're going to go down. Okay? So NO. NO is a what? Is it a reactant or a product? It's a product. So what's going to happen to that? That's going to go up. Okay? Let's keep going. Number 3. If we add water to the system, right here, which way is it going to shift? It's going to shift to the left, meaning reactants are going to start being produced and make more of those. Right? NO. Is NO a product or a reactant? It's a product. So what's going to happen to the concentration of this if we're shifting to the left? It's going to go down. Why? Because these are going to be used up more. Okay, your products, because again, this is where that forward and reverse, guys, it's not just looking left to right. We can go both ways with it. All right, so you got to think about what the effect is going to be for those. This is going up. Number 4, if we added nitrogen monoxide, which concentrations would decrease? This is a little bit different. You've got to think, even though it's not asking you where's the shift going to occur, you have to know where it is. So we're adding NO. Which way are we going to shift to equal out again? Toward the reactants, which is to the left is where we're going to shift. So which concentrations would decrease? The products, right? Which is going to be NO and H2O, right? Those concentrations will go down. Okay? Questions? Now, that, again, guys, if we increase the concentration, we go away from where the increase was. And that should make sense. Now we're going to do the opposite. What happens if we remove or decrease our concentration? Now we're going to go to where we decreased it. Okay? Now, if we decrease the concentration, we shift toward the side that has decreased its concentration. Toward. How do you say it? Toward.
You like mix forward and toward.
Yeah. How do you pronounce it?
Toward.
Yeah, I'm pronouncing the there's a W in there.
You pronounce
Toward.
it with the second R. You said toward.
Oh, whatever. Toward. Towards. All right, I'll just towards. All right. Here we go. There's our. Let's do an example together. If we remove oxygen, which side is oxygen on? Reactant. So now it's going down. You think about it visually, guys, again, like a seesaw. Here's my reactants, here's my products. We removed some of that. If I remove some weight over here, what's going to happen to my seesaw? It's going to go up like this, right? Because the product side would, quote unquote, be heavier. Which way has it got to shift now to get back to? See, it's hard for me because I'm like backwards to you guys, so it's got to shift this way. Right? Which is going toward where you took away the oxygen. So this is going to shift to the left. What's going to happen to the amount of ammonia? It's going to increase. Right? Because you're moving to where ammonia is. I want you guys to try number 2 on your own. Number 2, if we remove water, this is going down. Which way are we going to have to shift? I hear both. Which is it? It's going to go to where it was removed, so we're going to shift to the right. What's going to happen to the amount of NO? It's going to increase as you're going toward it. If we were to remove ammonia, okay, number 3, so it's not asking you for the equal or the shift, but you have to think about that first to answer the concentration question. If we take away ammonia, which way are we going to shift? To the left. What concentrations are going to increase? Oxygen. Oh, I'm sorry. I read number 4. Which ones are going to decrease in number 3? NO and water. You guys try number 4 really quick. We remove NO. Which way are we going to shift to?
Right.
Okay. What concentrations would increase then?
Ammonia and oxygen.
Nope.
Increase. Okay.
Yeah. NO and H2O, it's the same. Okay. Now here's the trick, guys. Think about it. AA, add away. Okay. You're going to shift. If you add something, you're going away from where you added it. If you take, you move towards. Okay. So TT, take, towards, AA, away, or add, away. Right? That's the way to remember concentration. All right? Now, pressure is another one we're going to talk about. Pressure, guys, as an initial stress. If we're talking about, guys, pressure in terms of being a stress, what can it only affect? Gases, okay? It can only affect gases. So if you don't have a gas in a reaction, this has no bearing on your equilibrium shifting. If we increase pressure, guys, we go to where the side has the least number of gas molecules, meaning the least number of moles. So you're looking at coefficients here with gases, right? If you increase pressure, you're going away from where the most moles are. If you decrease pressure, you shift toward the side with greatest number of moles, okay? Again, if there's no gas molecules, then there's no effect. You just say no shift, all right? All right, here we go. Here's our example. First off, look at the equation. Do we have gases?
Yes, we do.
Yeah? Are they all gases in there? No, right? So when we talk about pressure, guys, it's only going to affect what?
Yes.
Right. If we increase that. So if we increase the pressure, the concentrations of which species are going to increase? Right. So, but think about it. We said if we increase pressure, which side do we go to? We go to where there's the least number of gas molecules. Well, are there any gas molecules, guys, on the right side? It's going to actually start to go because you're going to start, by increasing the pressure, you're going to start using all this up. It's going to shift to the right with that. Does that make sense? Okay. Now, I don't anticipate you guys seeing one like this on your Regents exam. If they gave you one with gases, I would anticipate they all would be gases, like example number 2. So we're going to take this one with a grain of salt. Actually, you know what? We're going to skip on and move on from this one. All right? Let's go to example number 2 where they're all gases to start off with something a little bit simpler. All right? If we increase the pressure, in which direction will the equilibrium shift? So think about it. We're increasing the pressure, which means we're going to shift to where there are less moles. Well, we've got to add up the number of moles. So they're all gases here. How many moles of gas do I have on the left side? 4. How many do I have on the right? Which way am I going to shift to number 1? Yeah, we're going to shift to the right.
Oh, we don't count molecules? Or just saying.
Well, we are counting molecules because moles, right? Moles represent molecules. How many molecules are in 1 mole? Prize question. How many molecules are in a mole?
6.02 times.
Oh my gosh, come on! It's because the spring break was in there. All right. So 6.02 because so we can look at the number of moles, the coefficients, because that directly relates to the number of molecules. All right. If we increase the pressure, the concentration of which species will increase initially? So we already said, guys, if we increase the pressure, which side are we going to shift to? Tongue twisters. We're going to go to the right, so which substance is, I can't speak with this, which substance's concentration, guys, is going to increase? Ammonia. NH3. If we decrease the pressure, what's going to happen to our shift? We're going to go to the left, so the concentration of which species will decrease? Same thing, it's going to be ammonia. If we decrease the pressure, the concentration of which species will increase then? Right, nitrogen and hydrogen, guys. So, big thing is with gases, same idea of shifting, all right? It's just you're looking for gases, and if you increase, you go away, or you go to where there's less moles. If you decrease, you go to where there's more moles, okay? Last one is temperature. Guys, temperature is going to be very similar to concentration, because what are we going to look at for temperature? How do we know if we have a temperature aspect in our reaction? What measures temperature? Kinetic energy. So energy is what we're looking for. What are the 3 ways we could see energy or temperature in our reaction? We talked about this the other day. If you're given a reaction, how will you know you have energy there? What are you going to see? What terms would you see? Energy, heat, or something. What do you mean by enthalpy? Could have a delta. It's a value, like a kilojoule value, okay? Those are the things you're looking for. Like it says right here, heat, energy, joules, or kilojoules. Those are the pieces you're going to see. Most of the questions, by the way, right? If you guys haven't picked up by it, in the first 3 quarters, they're in your notes. Most of the questions I ask you. It's okay. So, we're looking for that term heat, or energy, or joules, or kilojoules, guys. When temperature is increased, you're going to shift away. So this is just like adding a reactant or a product. Okay? It's just like the first thing where we changed concentration. If you add, you go away. If you take, you go towards. Okay? Now, it also, though, helps us where we shift away, guys. It's in the endothermic direction, meaning back toward the reactants. If we go toward, it's the exothermic. Okay, so keep that in mind as we think about this. So, here's our example. It's the same reaction we had in part 1, but now we have heat added to it. Is heat a product or a reactant? It's a product. So what type of reaction is this?
Exo.
It's exothermic. So, if we add heat, which way are we going to shift? Away, right? So we're going to go toward the left. Which concentrations will decrease? NO and water. If we add heat, which concentrations will increase? Ammonia and oxygen. Easy? It's not too bad. You guys are going to practice this on Monday. Number 2, if we remove heat, where's my heat in example number 2? Kilojoules. There's my heat component. So we're taking that away. Which way are we going to shift to? To the left, towards it. What concentrations will decrease? And which ones will increase then? All right, I think you guys are starting to pick up on it. Awesome.